last week we had a time to check your mechanism. Some of the students came by, so I realized that there are two mistakes on grading, so I adjusted. So some of the students got more point, and the others, there's no one who deducted. So a couple of questions. So, and also I applied plus 15% for the curve of grading. So right now average is 65. So all students got 50 more points for the midterm. Okay. So which means some of the students is over 100. The over 100 will be the extra point. Okay, so this is mostly asked the question during the office hour. So this is a case of the three fork in a row. Okay, so let me quickly explain how many processes are created. In case of the 4 of them, like using the for loop, it's the same mechanism. You can add one more step. So this is the initial process. Initial process, the first time the fork. So I circle whenever the fork and proceed the next instruction. Okay. So that's the reason all of them has the square. So you can follow that step. So first the fork, this one. So at this moment there are two processes, P0, P1, and as we learned during the fork, it will be the clone. So P0 and P1 is the same, and the PC is the right after the fork 1, the first fork, program counter, and also this is the same thing. So process 0 will proceed the next instruction, fork 2. So by the second fork, the process 2 will be created. At the same time, P1 is proceeding the next the instruction. So this will be executed by fork 2 of the P1. The P3 will be created. At this moment, there are 4 processes. Okay, 4 processes are running concurrently, and the P0 will proceed the next one, fork 3. By the fork 3 of the P0, P4 will be created. Then at this moment, the program counter is after fork 3. So there are no more. But in case of the question that need the fork using the for loop, you can do the one more, the fork 4. So the P4 is done. So there is no more the fork, because the program counter is also copied. Is here. And at this time, using the fork P1 proceed the next one, P3, and also same time because this is the concurrent process after fork 2. So fork 3, using the fork 3 of P3, P7 will be created, and the P1, the fork 3, it will be created. Also P2, this after the fork 3, this one will be created. So total 8 processes will be created, including the initial processes. In case of the fork, you can do one more, and all of the 3 will proceed the next one. Okay, so this is nothing but I think the recursive, the creating. Then this is mostly average question, and another one is a synchronization. So using the test and set the instruction, we are going to show that this is the solution to address the problem of the busy waiting. In case of busy waiting, you need to keep checking. Okay, so that causes the overhead of the CPU. Instead, we will decide who is waiting, and that will be managed by the wait, the array. Then also during the while, the exit section. So we will check which one is the next one. The only difference from the textbook that we covered is that this one checking the minus downward. So you can see the minus one. So for example, in case of P2, there are several different variations of the problem, but it's the same mechanism. So current one is a P2. So P2, from the P2, it will minus, then check. If that is a 0, then go back to the last one, that is this routine. So currently P2. Then the next one is P1. P1 is a false, which means not waiting. Okay. Then going to the next one, minus 1, is the waiting. So P0 will be selected. So in case the P0 started, the current P0 is in critical section. The next one will be P4, but force the next one P3. So P3 will be selected in case the P0 is in the critical section, and so on. Okay, but if you just memorize the answer from the textbook, then you probably got the wrong answer because of this difference. Okay, any question? And also, couple of questions from the scheduling. So in the scheduling, so in case of most of the problem caused by during the round robin, okay, round robin, if the one round the quantum is completed, the current selected the process will be end of the reticule, okay. Then if there's a new process is added, and also that is the last one, then you can manage. But many of the students, if there is a new process, then select a new process for the next process. So many of the students select that. But there is always from the reticule, okay, which process is entered, the first one. So that if you check that part, you will found the solution. Anyway, so to adjust the average of the midterm exam, I apply the curve of grading by the 15 points. So you will see I'm going to delete, remove the quiz, the assignment, the midterm part, your grading book. So then you will see the new midterm, by after curve. So on canvas. So that is your final midterm grade. Okay. Any question regarding to the midterm exam? Okay. So okay. So homework. So please submit your homework before you leave. So because you already did your homework, so I'm going to quickly explain the solution of the other cases. So for your reminder, okay, so for the deadlock, so there are 4 requirements. First one is mutual exclusion. Okay, second is the weight, and third one is preemptive, and fourth one, so this weight should be circular the weight. So if for the modeling of the resource and the processes, we use the resource, the allocation graph, like the process request the resource, and the resource is allocated to the specific processes in case of multiple instances. So in this case, to define the deadlock, so we need to check whether all of these requirements are satisfied. But most of the case, for example, the mutual exclusion, for example, CPU, obviously only one process can take the CPU resource. And also the non-preemptive is already determined, like the printer can be non-preemptive. However, on the other hand, CPU is a preemptive. Always you can stop and context switch and select another process. Then the previous process can be selected again. It's always preemptive. And then we allow the holder weight. Mostly we are going to focus on whether it's a circular weight or not. So in case from the resource allocation graph, so if we can find the circular weight, okay, weight each other, circular weight, then maybe, not always, then maybe the deadlock. So otherwise, it's not the deadlock, it's called the safe state. So there are 4 solutions we discussed. One is, first solution, deadlock prevention. And second, avoidance. So today we are going to talk about deadlock detection. So deadlock prevention means we prevent these two approach never ever enter the deadlock situation. So before something happens, we need to check the previously. Then if it is suspicious or any chance to be a deadlock, we are not going to allow. So for example, prevention, there are 4 requirements of the deadlock. So we allow break at least one of these. For example, if the research is the shareable, it's not mutual exclusion, there is no deadlock. Well, another example is the hold and wait. So in case of hold and wait, we do not allow hold and wait. In other words, to proceed the next, to terminate the process, collect all the processes that you need. To do your project, you need the item 1, item 2, tool 1, tool 2, collect everything. Then when you are ready, then start do your project. Then there might be no problem. You don't have to wait until the other student the release the tool or the research. Okay, that is the hold and wait, right? The hold and wait. Non-preemptive, we are going to consider only the preemptive research. And the circular way is we are not going to allow any circular way. Okay, in other words, it's a serial processing, serialization. So serialization will be discussed more details in the database part. So database, they need to manage a lot of transactions. So it may cause the same problem. So at the time, it will be serializable. So by breaking one of these requirements, we can prevent the deadlock. But not always it is possible, right? For example, you cannot change the characteristic of the research, and also you cannot change the preemptive or non-preemptive research. So it's not always the possible. And also, for example, hold and wait. So you need to wait until collect all of the research, available research, and which is practically not easy. And also even the circular way is to find, it will be cost to find the serializable the processes. So that is the deadlock prevention. But anyway, you can prevent the deadlock. The second approach is using the bankers, the algorithm. Last time we model the process and the research using the research allocation graph. Then we have the process, number of process, and for the research number of the research type, each research type has the number of instances. So by adapting idea of the banker, as I explained in a bank, so they do not keep all the deposit money in their safe. Instead, they actually use the deposit money to the other customer to make the profit. At least you have the minimum amount of the money in case the customer requests. But at least the bank should be able to return the money for all customer requests one by one. So if you can do that, then otherwise it's a banker, right? If the bank cannot give the money to the customer, it will be bankrupt. So by adapting such an idea, if we can find the sequence of process P1, P2, P3, at least one sequence of process that can be terminated, then it is called the safe state. So safe state means there will not be any deadlock situation. On the other hand, if you cannot find such a sequence, which means sometimes it's stuck, it's waiting for the other. You do not have enough research. That maybe not always non-safe. It's not the deadlock always, but it's a maybe possibility to be a deadlock. So at the time you need to do something. That is the avoidance. The reason why it's called the avoidance means, so this is a current state. Each student is a process. Each student needs something tool or the item to complete the project. So this is a current status. So some of them are doing the project, some of them are not starting, but currently. But we have a very limited resource and the tool or the something item. So if the one student requests, I need a computer, then check whether this request will cause the deadlock or not. Who knows? The other student requests the same, the laptop or not. Okay? Then check before I give that the requested the item to the student. Check whether this will cause the, in case I accept, whether this will cause the deadlock or not. Okay? Then, in other words, in case I accept the request, whether I can find the safe sequence of a process or not. If I can find the sequence, it's okay. This request will be granted, accepted. Otherwise, no. This will cause the deadlock. So I cannot find the safe sequence of a process. Then decline the request. Then this computer system, operating system, will not enter deadlock. So this one never ever enter the deadlock situation. So for that Anchor's algorithm, so last time we have the one example very quickly. So before that we need to manage, obviously, we need to think about the available resources. For example, ABC is the three types of the, let's say the three types of the resource. A can be the, for example, the CPU. B is the hard disk drive. C is the magnetic tape, something like that. It's the type. And each one has the number of instances. How many CPU, how many magnetic tape, and how many the hard disk drive, something like that. Then we have the number of the processors. In this case, the 5 processors. Which means, so we can check the how many instances for each the process, for each the resource type needed, maximum to be terminated. The P1 to terminate the P0. P0 need maximum 7A, 5B, and 3C. Not at one time. Not at one time. From beginning of a process and terminating process, maximum it needs this amount. So currently, the P0 is using 1 of B. This is a current status. So to represent such a status, so we are going to define the data structure available. Okay? And how many instances are available for each resource type. And maximum for each process N and for each resource, how many of them are needed? Maximum. Okay? So it needs to be terminated. Allocation is currently allocated the number of instances for each process per the resource type. Then we can easily calculate how many needed in future to be terminated. How? It's a maximum minus allocation. Then we can easily get them. Okay, then these are the algorithm I ask you understand. So this algorithm, but best way, easiest way is using through the sample, the example. Then you can easily understand the meaning of this algorithm. So this is one of the example. So that we used. So at least you should be able to understand the current status. How many processes we have? 5. And how many types? 3 types. And for example, P0 currently it needs 2 of each resource type to be terminated. Currently, it has the 2 of A, 1 of B, 1 of C, which means to be terminated, how many more need? 0, 0, 1, 1. So, for example, P0 need, we can easily calculate the need. The max minus allocation, like the 7, 4, 3, and 1, 2, 2, 6, 0, 0, 0, 1, 1. And P4, 4, 3, 1 needed to be terminated. Then the available is 3, 3, 2 are currently available. Then the algorithm is very simple. So first we are going to find the process that is equal or less than available for each resource type. Is the P0 possible? No, it's you need the 7. So P1, Yes, 1 less than 3, 2 less than 3, 2 equal then to the C. So this is possible. 6, not possible. P3, possible. 0, 1, 1 is less than 3, 3, 2. And the P4, not possible. So we can start either P1, P3. So it's up to you which one is the first. Okay? But the idea is just the T. If that return the more research, that will be better. Like the P1 currently has a 2, 0, 0. P3 has 2, 1, 1. So we can start the P3. But later, in case P3 is stopped, we can go back and start again for the P1. So let's start with the P3. So P3 is done. In case P3 is done, then 2, 1, 1. This one will be returned free and will be available. Total available will be what? 5, 4, 3 is currently available after P3 is done. Then we are going to find the same thing among the current processes which has the equal or less than the available resource. 7, this is not possible. P1 definitely possible because it was possible before. And this is not possible. And this is possible. So we can start the P1. So P1, once P1 is done, and P1 has the 2, 0, 0. So 2, 0, 0 will be added to the available. So P1 is possible. 7, 4, 3, all of them are possible, right? It's equal or less than 7, 4, 3. So P0, P2, P4. So we can find at least one safe sequence of the processes to be terminated with this condition. Then, which means this is the safe state. So using this idea, this Banker's algorithm, so we are going to apply this approach to the avoidance. Actually, the deadlock detection is the same algorithm we are going to use. So, in this case, P1 requests 1 or 2, which means 1 A, 0 the B, 2 over C, which means among the needed, it will be 1 or 2. 1 or 2 is suppose that this request is accepted, whether this one is safe or not, using Banker's algorithm. So this one is accepted and the allocation will be changed. So this is a P1. And the others are the same. So available right now 2, 3, 0. This is the case, the status if we accept the request of the 1 or 2 for P1. Okay? So at that time, can we find the process list that will be terminated successfully? Fine. So this one is not possible. Is this possible? Yes, 0, 2, 0 is less than this. This one is not possible. And P3 is not possible because it needs at least one C, but there's no available C. Is this the one? Okay, so only P1 is possible. So in case P1 is done, 3 or 2 will be returned because that is the allocated. So 5, 3, 2. So in case of the 5, the 3, 2, not possible, not possible. But this one and this one is possible to be terminated. So we can terminate the P3. So P3 is a 2, 1, 1, 7, 4, 3, 7, 4, 3, and 7, 4, 3, 7. All of P2, P0, P4 will be one sequence. That may be different. It doesn't matter. Okay? As long as you found the one, the available safe sequence, that's done. In your exam, for example, if I ask you to prove why this one is granted, then you can show at least one sequence of a process state. Okay? Then, so this is in this case, does operating system grant the request of the P1 or not? Yes or no? Yes, because there might be no problem. So you accept, grant. So allocate, really allocate. This time we pretend before enter the next step of the request. Before that, we check. Suppose that whether this request causes a problem or not. There might be no problem. Then okay, we grant. But another example is the 330. For example, 330. So let's say using the previous case, not this one. Available 332. So this is a 3, 2, 2. No, it's a 1. It's a need. Where is the need? Need is 7, 4, 3, 1, 2, 2, 6, 0, 0, 0, 1, 1, 4, 3, 1. Okay. Then, in case the P4 request 3, 3, 0. Okay. Then the P4, if we allocate the 3, 3, 0, suppose that we accept this request. So 1, 0, 1. Okay, then it will be 0, 0. This is the 3, 3, 2. It's allocated. Suppose that we accept this request. Then this one, process state will be like this. Or this one should be 0, 0, 2 available. Is this safe state or not? By using Banker's algorithm. So we are going to find the sequence of process state. Okay, which one will be possible? No one. Okay, this one very close, but we need at least the one of A and B, but no available. This one. So which means this request will be declined. Why? In May. We are not sure whether this is really the deadlock one. It's a high possibility to be deadlocked, so we declined this request. So system will not enter the deadlock situation. So you can do the same thing for this one. So in your homework, you probably did. Okay. Then the first approach is prevention and avoidance. The operating system never allowed to enter the deadlock situation. But so we need to check that every time. Whenever there is a request, there is a instruction that used something, the resource, it will be overhead. Okay. So to address that problem, we allow grant any request. Also, even though we do not find the safe sequence of processes in the Banker's algorithm, it's not always the deadlock. Sometimes deadlock, sometimes not. So we grant any request. Then instead, this is the time. From time periodically, from time to time, we are going to detect whether there exists the deadlock situation or not. Okay, this is kind of the example of, I'm not sure whether this is a good example or not. So in the classroom, as an instructor, let's think about that this is an elementary kindergarten classroom. So I'm responsible to manage the student kids, right? So whenever the student request or do something, I need to check whether this action causes a problem or not. How many students? I have the 70 students. It will not be possible to check. It takes a long time. So just let them play or do anything. Then from time to time check whether there exists any problem or not. Okay? If I can detect a certain problem, then resolve it. Not every time, periodically, every hour, check whether there exists problem in this classroom or not. So that is the deadlock detection. Periodically check the system status, whether there exists the problem or not, deadlock or not, which is called the deadlock detection. How can the operating system detect the deadlock? Using same resource allocation graph and using Banker's algorithm. We are going to use the exactly same algorithm that we use in the deadlock avoidance. At this time, we don't have to worry about the request. We always allow the request just a certain time. The process allocation, the process and the resource status, using this status, check. Is there any the deadlock one? How can we check? Using Banker's algorithm. In other words, whether we can find sequence of process or not. So that is the deadlock detection. So we are going to use the same data structure that we defined in the Banker's algorithm in the avoidance. It's the same algorithm as the Banker's algorithm actually. So as you can see, so we have the allocation request available. So even though in this case the no available resource, it doesn't mean that it's a deadlock. Okay, we can find the process. For example, available here. Request. Available is 000 and the normal request. Okay? Which means P0 can be terminated because there is no more request. Also, P3 can be, P2 can be terminated. So by combining 3A, 1B, 3C are available. Okay? Then we can find the processor that is equal to less than 3, 1, 3. This one is less than that, this one is less than that, this one is less than that. So which means there is no deadlock in this status of the operating system. Okay? Because we can find the sequence of the process. Then this is a different cases, so you can find whether there exists a deadlock or not. In case of the deadlock, what is the solution? How can we, so for example, deadlock prevention, deadlock avoidance, the system will not enter deadlock, never ever. So it's not a problem. So, but problem is it takes a time to decide. So whenever there is a request by the process, we need to check whether there is a deadlock or not. But the deadlock detection allows all the requests, but from time to time we need to check. So it is possible there will be the deadlock. So we can find that this is there is a deadlock. What will be the solution? We need to solve. How to solve? So if there is any problem in this classroom, the only solution is kick out the student, right? Then it will be perfect solution. So kill the processes. So that is the usual, the normal, the solution. Then, which is called the victim process. The problem is how to decide the victim. Okay? So he is a very nice student, even though he is involved in the problem. So I try to kill. So or any process that involves the deadlock, we decide all process as a victim. We kill falsely terminate all the process. So problem is how to determine the victim process and how do you decide which process will be victim? You need to